Hi, everybody. Thanks again for tuning in to the Urban Water Innovation Network Science Talk webinar series. These rounds of presentations are focusing on key findings of the 5-year research projects with a distinct emphasis on pragmatic recommendations for stakeholders and practitioners. So we recently shifted gears to focus on the impacts of innovative technological solutions for urban water systems under Research Thrust B. As y'all know, we are recording the webinars and I will post those to our YouTube channel and the UN website. So you can feel free to check back there for links to anything you may have missed. We're also hoping to have a good discussion at the end of the presentation today. So feel free to throw your webcam on, turn your mic on, or enter anything into the chat queue and we can get to that at the end of the presentation. So I am excited to introduce today Dr. Thomas Meixner, Professor and Department Head of Hydrology and Atmospheric Science at the University of Arizona. Dr. Meixner's research lies at the intersection of hydrology and biogeochemistry. In particular, he is interested in how hydrologic processes play a fundamental role in controlling biogeochemical processes and fluxes at the catchment scale. Tom's research group spans from field investigations designed to understand these controls at the mechanistic and process level to modeling studies focused on forecasting biogeochemical and water quality conditions at the catchment to basin scale. The modeling side of his group works on developing model calibration and uncertainty techniques that can coexist with both multidimensional and yet sparse data that is typically available for water quality modeling at the basin to catchment scale. Tom's work has spanned environments as diverse as desert scrub and alpine ecosystems, and from scales of single soil profiles to 10,000 square kilometer catchments. So with that, Tom, I will hand it over to you.
Thank you, Sarah. Did I write that?
Yeah, it's on your faculty.
That's what I do. That's good. It's a good reminder. So I appreciate it. Thanks for the great introduction, Sarah. So I'm going to talk particularly about green stormwater infrastructure today and some of the progress that myself and what I'll try to impress over time is the really large set of really great colleagues and collaborators I've been able to work with. Because clearly all the work presented today isn't my own necessarily, but it's the result of a team effort. And so, you know, what was learned and what we're doing, so that I'm not going to talk as much about this biogeochemical activity today, but maintenance can decrease function. GI has a significant hydrologic impact, but hasn't gotten there yet in Tucson, and I suspect most places. And then sort of finishing up today, I'll talk about cities differing in practices, but they share a lot of common goals and methods in terms of how they build and design green stormwater infrastructure. Okay, so some of the context and background here is that in the Colorado River Basin, where Tucson finds itself, and a lot of the western United States is in a similar situation, we're in a situation where water demand has exceeded water supply. And there's a variety of different causes of that. But one of the things I want to sort of remind us of is sort of what we've accomplished so far. And that's that we've actually decoupled economic and population growth from total water withdrawals from the environment. This is, you know, USGS data, not with the 2015, but I'll note that in 2015, the total water withdrawals in the United States declined further to about 380 million acre feet per year. Under the USGS data. So, you know, water usage in the withdrawals in the United States actually peaked in the 1970s and 80s. And we've been declining usage ever since then. And we even see that at the local scale here in Arizona, particularly in Tucson, where water deliveries back in the 1980s were about 170 gallons per person per day, GPCD. And today they're down around 116 gallons per person per day. In fact, they're closer to about 100 now. And that's in the single family home sector. So we've dramatically declined the amount of water we're using on a per capita basis. And in fact, total withdrawals and total usage in Tucson has peaked in the early 2000s. But part of what drives my research is, where's that next bucket of water going to come from to further decrease these withdrawals from the environment, or at least reshuffle those withdrawals? And that's where green stormwater infrastructure comes in. Okay. And one of the realities in cities is that we know that cities, and this is from a publication actually from a UC Irvine and Melbourne group, right? We know that cities profoundly change the hydrology of the watersheds in which those cities are built. flood flow increases. We change the morphology of our channels, often lining them with concrete or at least straightening them. We have water quality and ecological impacts of that. And the drivers of that are the increased imperviousness, the formal drainage network, the stream modification, and the fact that we import water into cities. But a key here is that for our water resources challenges, these drivers and these symptoms of the urban stream syndrome actually align with our need to divert less water from nature and if you will, put the water in our cities to work where it is, as opposed to just conveying it away as a waste product. So, and that takes the form of unlined biofilters, which is largely what I'll talk about today, is sort of biofilter systems, but also rainwater tanks. But there are other strategies too, green roofs, permeable pavements, things that slow and dampen event response and the transformation of rainfall into runoff in our cities are all components of sort of how we solve this urban stream syndrome, but also notably how we can help solve some of our water resources challenges that we particularly have in our arid and semi-arid cities. So in Tucson, what that looks like is that on this figure here, right, the amount of runoff that we generate depends on drainage size. So this fraction of harvestable rainfall, you could also just think of as runoff ratio. But at small drainage sizes, roofs, neighborhoods, the amount of runoff in our undeveloped watersheds is relatively small. It's maybe 10% of rainfall gets converted into runoff. But in our urban environments, it's more like 30, 40, 50%. And from roofs, about 85% of rainfall gets transformed into runoff. So there's this diversion between our urban areas, which have more runoff, than our undeveloped areas. And in particular, our cities have, when it rains, this B figure here is showing you that when it rains, about 70% of the time that rain produces runoff, whereas in our undeveloped watersheds is about 20%. And in our cities, when runoff occurs, it occurs for a longer period of time in our cities in arid and semi-arid areas, averaging about 4 hours of runoff duration versus only less than 2 hours in our undeveloped watersheds. So this is simply to point out that in our cities, when it rains, we get more runoff, more often for a longer period of time. And that combination indicates that there's perhaps a capturable resource there that can help solve some of our water resources challenges that we have in our arid and semi-arid cities. Okay. And so our hypothesis is, right, we have this undeveloped watershed where discharge is less for a shorter period of time. We now have these developed watersheds where more runoff occurs for a longer period of time, more often. And that maybe with green infrastructure, we can start taking that developed hydrograph and make it look a little bit more like that undeveloped hydrograph. And, the first question that we'll approach is, how much water is that? And how feasible is that transformation going to be, or could it be? Okay. And this work actually starts with some SWOT modeling, so very large scale runoff modeling that a PhD student of mine, Rawati Narala, did with Laura Norman at the USGS. And we looked at different land cover projections, but essentially, right, Tucson, Arizona, Sun Corridor of Arizona, we're expecting continued population growth, continuing sprawl. That sprawl can take different forms, but ultimately greater imperviousness across the region. And we're looking at 30 to 40% increase in urban area over, well, now the remaining 30 years between now and 2050. And what we saw in that work was, if you will, that the total flow increase of the Santa Cruz River Basin as a whole would be about 42,000 acre feet per year. Okay. Now, this is notable because it's that 42,000 acre feet per year, total Tucson water potable delivery to about 500,000 people every year is about 100,000 acre feet. So 42,000 acre feet isn't going to provide all the water for all those new people who are moving in and creating that greater impervious cover, but it is an element of a solution for the water resources challenge. And notably also that 42,000 acre feet isn't all necessarily recoverable. Because in particular, the watersheds where we saw the greatest flow increase on the y-axis, so this is change in stream flow occurring in the various subbasins of the watershed, was greatest in the areas that had the largest urban area increase, which is what the x-axis is here. And particularly, there's this sort of breakpoint, somewhere around 20 to 30 square kilometers of urban area increase. That's when you start to see this bump up in stream flow. So there is a network effect. Okay. So what we were trying to do as part of UN is then understand, okay, if we're going to have this greater urban runoff, what strategies might there be to capture that runoff and put it to water resources purposes for people, particularly for landscape irrigation and urban canopy, sort of treating inside the house water differently than outside, which is a reasonable approach to take, because water that you use inside your house goes to a treatment plant and conceptually could be reused sort of as part of the ongoing activities. Water you use and irrigate outside essentially goes back to the atmosphere and can't be put to another use within the region. Okay, so to pursue these questions, we used a model called Kenrose. Yoga Korgaonkar and Phil Gerton sort of led this work. And Kenrose is a pretty simple rainfall runoff model that breaks a watershed up into constituent hill slopes, sort of illustrated here. You might have a real catchment like this, break it up into essentially uniform hill slopes that will transform rainfall into runoff. And it's a model useful for smaller watersheds. And one of the reasons we use this model in particular was that Yoga, Dave Goodrich at the USDA Ag Research Service and others have built into this model an urban component, and particular the GI practices, green infrastructure practices within a location, and have enabled the devising of directly connected pervious surfaces, indirectly connected impervious surfaces. So roofs that run into yards, or roofs that run onto driveways that run into streets, and also built-in retention basins. But the key here is that we have a way to transform sort of bioswales and pervious surfaces in the real world into sort of the abstract nature of a rainfall runoff model in the watershed. We then took this model and modeled a particular watershed here in the Tucson region, the high school wash watershed, which includes in part the University of Arizona campus, where I am currently sitting in this building. There's this big white roof, that's our student union. I'm in this building just to the north and west of that. So, and the very corner actually. So this is it's a small watershed, but not too small. It's about 3 square kilometers here in Tucson. And notably, the watershed it's fairly typical of the watersheds in the Tucson region. About a quarter of the watershed is actually roofs. A quarter of the watershed is streets. And about 16% is other impervious surfaces, parking lots, driveways, things like that. Okay, so the total impervious area of the watershed is about 2 square kilometers. So about 2/3 to 3/4 of the watershed is impervious surface. So impervious surfaces, rain's going to come in and it's going to immediately get transitioned into runoff for the most part. There might be some absorption of low intensity rain events. So this is a typical watershed here in Tucson. And so the first thing Yoga did was say, okay, we'll model this watershed as is with what its current GI is, which there's been some implementation in this watershed. And we'll model this watershed with doubling that green infrastructure, increasing that green infrastructure by a factor of 5. We'll model the watershed pre-development if it were a native rangeland, okay? And if we put GI absolutely everywhere possible, we're gonna put rainwater cisterns on every roof. We're gonna put GI basins on every block, in every yard, and capture the maximum amount of rainfall. And then this figure here shows those simulations with and without versus a no GI simulation. Okay, so we have current, like I said, through 5 times, a pre-development simulation, and then max GI. Okay, and what we're looking at here are the 1-hour storms for a 5-year return, 25-year return, and 100-year return interval. Okay, and what we see with current GI, we have peak flow and then total runoff volume under each of these storm types. Okay, and the storm characteristics for what that 1-hour storm are up on the upper left. Okay, and what you see is actually peak flow actually increases slightly. Now this is a percentage increase, so I think we can agree that 0.23% increase or 1% decrease in volume are essentially no effect. But the point is that the current level of GI deployment in this watershed, which I want to note, this watershed was in part picked because there has been somewhat significant GI deployed in this watershed. It has a negligible effect on peak flows or on total runoff volume. But notably, doubling that or quintupling it does start to have a significant effect on peak flow. So 20% decrease in peak flow, across the storm types for 5 times. And that seems like a reasonable thing, like that's possible. Now, max GI, we could essentially capture the entire 5-year storm. In fact, capture almost the whole 100-year storm if we put GI everywhere. So this is, quote unquote, the sponge city scenario that people in China have advocated for. So in Tucson, at least, it looks like that you really could turn the city into a sponge that just absorbs all the runoff. Now, that's an unlikely scenario for a variety of different implementation reasons. But 5 times is not unreasonable, and 2 times is certainly doable. It wouldn't require significantly more effort than now. So we're not yet having an impact on flood flows, and you'll see that with some data a little bit later, but we're not far away from actually having an impact on flood flows and volumes. So what does this look like spatially? So here on the top, you have that current GI implementation. And what you're looking at is sort of on the left, the percent reduction in runoff on a street compared to without GI implementation. And you do see some effect of GI implementation, some volumes up to about 25 cubic meters on a streetscape scale, okay? In the center, what you're looking at is the actual GI configuration. How much of these are retention basins? How much of this is rainwater cisterns? So cisterns are shown with these green dots, the basins in the orange, okay? And on the right, you're looking at that rainwater that's captured by the cistern or infiltrated in a basin. So, some larger basins are actually able to absorb that, 25 cubic meters or so, okay? So that's current GI. And I'm gonna just skip to the 5 times implementation, okay? And here you see, right, 5 times implementation would be, if we compare this to this one, right? This is a sparse implementation that's currently been done. If we go to 5 times, we're talking about implementation. Most places in the watershed, most runoff is at least going to have the opportunity to hit a retention basin or a rainwater cistern in the catchment. And then this is all 3 scenarios, okay? And you can see as we increase deployment of GI, we see more and more implementation across the watershed. But like I said, at 5 times, you're really looking at a raindrop is going to run into something somewhere. And we saw that in the total volume and peak discharge. And just some backup of this with data we have, comparing the Bronx watershed on the right here to the high school wash watershed on the left. And notably, both watersheds have had significant implementation of rainwater harvesting, but notably in the lower parts of each of the 2 watersheds. And I want to sort of emphasize this figure on the right, which shows Bronx on the left and high school on the right on the 2. And in the winter, we do see some effect of decreasing runoff in the high school wash watershed, but we really see no changes in runoff in the Bronx watershed. And this despite some rather significant GI implementation. And this has led us to the conclusion that likely what we're seeing in high school, particularly for the lower intensity winter storm events we get, is that what we're seeing is an effect of the fact that in the high school wash watershed, the wash is unlined. And so you're getting interception of runoff and infiltration along the channel, whereas the Bronx watershed, the channel is completely lined. So this is sort of a reminder that we're implementing this green stormwater infrastructure attempting to do it at the catchment scale. But perhaps the most important GI we currently have in Tucson is the unlined washes that are present in the city. Okay, so in addition to that analysis that Yoga did of rainfall runoff response at the catchment scale, he also did an analysis of, if you will, water resources. So he did a 20-year simulation across the watershed of how much water is being intercepted by these rainwater cisterns, how much is being intercepted by these basins, and how much of that water is going into daily water use of evapotranspiration demand. So he sort of did the whole layout of okay, here's our on-street, you know, and he only did this for the current GI simulation, but here's how much on-street basins there are, here's where the rainwater cisterns are. How much of water use could these systems actually meet? Okay, and I'm not going to show you, you know, the full drawn out of the data, but I think this one lot gives an illustration of how this plays out. Okay, and so here we have, you know, demand on the top. Okay, essentially how much water is demand on a monthly basis. And right, demand increases in the dry foresummer we have here in Arizona. Doesn't rain in May and June. The atmosphere is dry. It's really hot every day. And then it declines as we go into winter with shorter day length, plant senescence, plants going dormant. And on the bottom, what you're looking at is a cistern. Okay. And you can see the cistern fills up during our monsoon season most years. It's filled. And it stays often filled during the winter rainy season and then empties out, okay? And empties out during that dry foresummer period. And the cistern does actually completely dry out most years in that May, June period before summer rains start. And, you know, this is a fairly typical parcel in Tucson, single family home, some impervious roof area, but landscape use as well. So, you know, we're able to meet most of the landscape demand for water with a sizable cistern here, right? This is not a small cistern, 1,300 gallons of storage, 5 cubic meters. But we're able to meet most of the irrigation demand on this lot with this, except for this dry foresummer period. Now, notably, Yoga's simulation here didn't also account for the fact that there is soil moisture present that might support that vegetation as well. But you can see that dry foresummer May, June period is a challenge here in Tucson and other dry periods. If you're in Southern California, you have to keep that cistern water for an entire summer, which is probably not feasible. Okay. Another analysis he did was of these on-street basins. Okay, could an on-street basin actually meet the water demand of a tree planted in them? Okay, and so here you're looking at, in green, the average infiltration on a monthly basis across the year, and this is a 20-year average. And the blue is actually the demand from that tree. And what you see is that on average, over that 20-year period, every month has more infiltration in a given month than the actual plant water demand. Another way of saying that is simply the green bars are bigger than the blue bars, except for the month of June. Again, when plant water demand is highest and we're reliably the driest time of the year in terms of rainfall. So on-street basins could actually meet most of the irrigation water demand, particularly if you take water from the summer and winter rainy seasons in the soil moisture and provide that to the trees. So this then becomes a question, well, how do we define a functional bioswale? Okay, so this, now we're going to go back to the field data. So, right, what defines an effective bioswale? Well, first of all, the one on the left is effective. It's actually filled up with rainwater when it's rained. The one on the right is ineffective, right? It's dry, and that's because the channel going into it is clogged up. And we'll come back to that later when we talk about actual observations of bioswales in individual cities and across cities. Okay. But these bioswales are fairly typical design here in Arizona. And what I'm talking about now is some work of some master students, Samantha Swartz, Victoria Hermosia, and Jack Anderson in my group over the last several years. But right, we capture water off the street, we use it to water a basin that has some plants and a tree that provides some shade to mitigate some of the urban heat effects that Matt studies, that David Handula has talked about, that Forrest has talked about. Okay. Now in Tucson, sort of neighborhood scale stormwater harvesting has been advocated, and we have some grants, and these grants are facilitated by a group called Tucson Clean and Beautiful, who then advises people how to maintain these basins. Okay, well, they advise that people maintain these basins by removing trash, pulling weeds and invasive grasses, and pruning the plants, sort of as typified here. Well, that maintenance takes a variety of forms. But you can see here some what would be classified as well-maintained basins. They've been raked, they've been cleaned, the plants have been pruned, there's no trash present. They look nice and neat and tidy. So aesthetically, they're pleasing and they have what my landscape architecture colleague Bo Yang calls cues to care. They look cared for. And in general, aesthetically, people like landscapes that appear to be cared for, almost no matter what they look like. But people want to say, oh, people live here, they take care of these landscapes. But all bioswales don't look like that, right? Some bioswales are less well cared for, okay? And they have some weeds present. They appear to, maybe someone occasionally pays attention to them, maybe not, okay? And then we have sort of poorly maintained basins, even more weeds, maybe the plants aren't pruned, maybe there's trash present. So Samantha decided to investigate these basins and their hydraulic properties using a subjective determination of well cared for, poorly cared for, somewhere in between. And she used something called a Solecore air permeator. And the reason I bring this up is it enabled her to quickly capture data on permittivity and hydraulic conductivity as a result. You know, she was able to get sort of a thesis worth of data with about 6 weekends of worth of work, and then the ensuing analysis. Okay. And you know, there's a equipment that's used for this to give you an illustration. But the take home of her data is shown here on this figure. So on the left, we have well-maintained basins. On the right, we have poorly maintained basins. And in the bars, we have the individual data points. And in the averages, so the average hydraulic connectivity of the well-maintained basins to the poorly maintained basins, and the variation. And what you see here ultimately is that the well-maintained basins have an average hydraulic connectivity of about 2 centimeters per hour. The poorly maintained basins have a hydraulic connectivity of about 3 centimeters per hour. Okay. So poorly maintained basins actually have higher hydraulic connectivity on average than well-maintained basins, which is a little bit of a counterintuitive result because we intuitively, well, things that are well-maintained should have better function. But a key here is that the function that's being judged here is hydrologic, and the quality is being judged by aesthetics, like which basin looks better. And a different way to look at this data is the hydraulic connectivity sort of distributed, you know, how does it vary across all the basins? And again, the well-maintained basins have not just lower average hydraulic connectivity, but across the distribution have lower hydraulic connectivity than the poorly or fairly maintained basins. So what exactly is going on here? So our recommendations for this are, well, look, maintenance is needed. People need to see cues to care that basins appear to be cared for. But our hypothesis is a lot of the care that's recommended right now involves the removal of organic matter. And organic matter, we know, improves water holding capacity, improves soil structure, all of which can go to increasing infiltration rates and hydraulic connectivities. So, you know, people need to not necessarily remove all that organic matter. Maybe these basins need to have some denser vegetation, add organic matter when they're originally designed, and this layer of organic mulch. So that data was all for Tucson, okay? And you might assume, and rightly so, that Tucson is not a representative city of every city, say, in North America or the world. And for this, I'm going to go out to some research work that I've done with a variety of collaborators at City University of New York, particularly Jennifer Thierry on the upper right. Brian Smith originally helped design this project. Alan Berkowitz, Jose Padilla, you know, and then me. And our research team changed over the years. We added some people, Allison Downey and others. But we did work across a set of cities across North America with the collaboration of Earthwatch, a nonprofit NGO that focuses on citizen science, and the bank, HSBC. So which is why these cities end up being selected, right? We worked in New York City, Buffalo, Toronto, Chicago, Vancouver, British Columbia, and San Francisco, California. Now, all these cities had efforts in incorporating green infrastructure and bioswales, and they all had combined sewer overflows, which is in part why they probably had a significant green infrastructure effort. Now, we did citizen science effort. We sort of did these one-day campaigns, and part of it was to see if a protocol with citizen scientists would work. Okay, and so just sort of comparing two methods, sort of boxes and swale area from mapping, this is to give you an idea sort of the size of these bioswales, right? Some cities like San Francisco and Toronto had very large bioswales, 50, 60 square meters. Some cities like New York City had small bioswales. Now that's not an accident. New York City's some of the most expensive real estate in the world. Land's at a premium. We might expect green infrastructure has to have a smaller footprint. And lo and behold, that comes out in our data. But also, right, why is Buffalo with lower real estate property values than, say, Vancouver or San Francisco have smaller bioswales? Some of that's a result of the places in the cities we went to, right? Buffalo and Chicago were central business district. Toronto and Vancouver were outlying areas in the city, as was the case with San Francisco. Okay. And these citizen scientists were able to collect good data on GI features. So here we're just looking at, ground cover. So Buffalo and Chicago had a lot of bare area. San Francisco, Toronto were a lot of vegetated area. Different aesthetic choices across different cities. Okay. And across these cities, we also had sort of different GI features as amenities, like how pretty they were. So Buffalo's bioswales were actually considered to be among the more beautiful versus San Francisco and Chicago's. In Chicago, maybe the reason that aesthetic rating is lower is a lot of the plants were dead. And then across the cities, we're able to assess this. Were the bioswales, were the entries blocked? Were they unblocked? And again, Vancouver and Buffalo performed well, largely unblocked entries into the bioswales versus New York City, where a lot of those entries were blocked. Okay. As disamenities, how much trash did people observe? Were the plants trimmed? Again, variation across the cities. So the results of this on the amenities sort of side of things were, these bioswales sort of worked. Okay. On the function of these, we're able to compare the field data that people collected for hydraulic connectivity in the field using a simple permeameter to our laboratory observations of hydraulic connectivity. And again, the field data is different than the lab data, and there are differences across the cities. Buffalo, in particular, notably has higher hydraulic connectivity. But the citizen scientists on a one-day campaign were able to actually get a pretty good idea of what the function of these bioswales was pretty quickly. And so the result, if you will, writ large, was that citizen science protocol worked. And notably, the citizen scientists were also able to implement, install sort of GI sensors of soil moisture and function of these GI on a one-day campaign. So our citizen science protocol across these cities turned out to be relatively successful. And I can tell you it's been further successful. It's been used as a model here in Tucson by the city of Tucson and Tucson Water to do some monitoring on an ongoing basis by citizen scientists. But that's one snapshot of 6 cities. Working with Aditi Bhaskar at Colorado State and her grad student, Ben Choate, we were able to look at GI across a very large number of cities by pulling together data from, I'm not even going to try to list the number of collaborators, across a number of cities all across the United States. And here's just a simple figure showing the total stormwater control measures by city. So you can see Washington, D.C. and Portland and Philadelphia and New York, Austin, Texas are among the leaders. Okay. Several of those cities, Portland, D.C. and New York, share combined sewer overflows. And that turns out to be a key element, that cities with combined sewer overflows have implemented a lot more stormwater control measures, and that's probably not an accident. Combined sewer overflows, raw sewage in your city harbor, your city river are bad, and people have responded likewise to try to minimize the occurrence of those using green infrastructure as one measure, in part because green infrastructure is a lot cheaper than some of the big traditional gray infrastructure, big storage containers, big reservoirs that can contain stormwater and sewer water until the treatment plant can catch up after a storm. And just to give you an idea of the diversity of efforts, right? The the color palette here is giving you an idea of different types of basins. So blue is basins and filters. Orange and red are swales and rainwater harvesting. Red is rain gardens and pervious pavement. And then infiltration and green roofs in green. But I don't want you to sort of focus in on any individual city here, then just to sort of first go, gosh, cities' efforts vary quite dramatically from one place to the next. That's probably an element of climate, an element of culture and socioeconomic capability of, financial capability of cities, right? Some things like bioswales are cheaper to implement than, retention basins and the like. Whereas, retention basins might work better in a drier climate, and infiltration might work better in a drier climate like Phoenix. But Ben's done a good job of analyzing this data across this diverse number of cities. But one of the very real challenges he had was sort of classifying these cities, what these cities called things, into an actual database of comparison across those cities. And then classifying those cities, cities like Portland and Washington, D.C. and Philly, having a consent decree. Yes, that's what yes means here. And then phase 1 or phase 2 of sort of MS4 permits. Do they yes or no have combined sewer overflows? And are they in phase 1 or phase 2 of an MS4 water quality permitting from the USDA? Okay. So comparing these cities and sort of thinking about them, right? GI is quite diverse within and across cities. There's a maintenance interaction with design, and that impacts function across these cities. And the scale of GI implementation, needs to be tempered with realistic goals. If we go back to Yoga's modeling, we saw that, yeah, you could implement GI everywhere all the time and capture every raindrop. But feasibility-wise, that's not likely to happen. Some homeowners or neighborhoods won't necessarily want to cooperate. Some places might turn out to not be feasible. From Ben's results, it's clear that combined sewer overflows, water resources demand, flooding, and other factors influence implementation of GI. And then there's this regularization of nomenclature that it's kind of hard to go into detail and talk, but I can tell you Ben struggled mightily with what do we call these things, and how do we coordinate what's called a bioswale in one city, and it's called a rain garden in another, and called a detention basin in a third. And sort of to wrap up, right, we have these GI systems. Well, let me go back. So one effort that's grown out of this is an effort with colleagues here at the University of Arizona, led by Courtney Crossan in architecture, to sort of go after what we've called a net zero urban water framework. Are there ways we can rethink the availability of water in cities? And green stormwater infrastructure deploys one of these, to think about how we can get cities to a net zero water footprint vis-a-vis its environment, right? People obviously need to use water, they need to extract it from the environment, but can we do that in a way that puts the footprint of water for our cities at a net zero? And I think this is likely not a achievable goal, but I think it is a useful goal to keep in mind, that if we can find ways to put to use water in our cities, whether it's reused wastewater effluent, whether it's reused stormwater, whether it's making our cities more water efficient and conservative, that it serves to focus our mind around, well, what is this water we're using? What use are we putting it to? What water is available to meet that use? And, at a bigger picture level, right, we need to think about, so GI can meet this role of outdoor water use and reduce outdoor irrigation water demand from potable sources, and maybe decrease flood risk. But human decisions are going to play a key role in this. What's the role of design and maintenance? Like we saw in Sam Schwartz's results, the function of these GI systems isn't constant in time. How we maintain them and choose to maintain them is important. And that implies a role for policy, culture, economics, sort of the wide diversity of human society in implementing and maintaining these systems. And with that, I will finish and I would love to have a broader discussion with everybody. And I'll stop sharing, and if I need to share, I'll come back to sharing as needed. So thank you all for listening, and appreciate your time.
Great. Thank you, Tom. You guys have been so busy. Lots.
Yeah, it's been a lot of work. So, yeah.
Great. Well, anybody have questions or comments for Tom?
I have a question.
Sure.
So thank you so much for your presentation. I really appreciate it and learned so much on it. I had one question about what scale are the GI implemented? Is it going to be public, private, block scale?
Yeah, so I think, within Tucson, the context is generally neighborhood and individual lot or residence scale. So they're not large integrated GI systems. We do have some of those, but what I focused the research on here is sort of this small scale residential lot or street scale implementation.
Okay, and so I guess since they're for more private, so does that mean that there's also difficulty to convince people to?
Yeah, so it is right. People are individually implementing this or collectively implementing at a neighborhood scale. So there is an element, if you will, of persuasion and convincing, and variable uptake across the city. Right, some neighborhoods have jumped in with both feet. Some neighborhoods are resistant. Some residences are very embracing of it. Some are not, and there are both cultural and socioeconomic factors there, that have caused variable. But some of it's just some neighborhoods have a champion, some don't. So.
That's fair. Thank you so much.
You're welcome.
Tom, question from DC to New York City. We've just been pummeled,
right,
by big floods, and so even in the settings with combined sewer, the big topic is climate change and flood hazards.
Yeah.
Give your thoughts on where green infrastructure will play into this. I know it's on everybody's mind out this way.
Sure. Yeah, I mean, you guys had those, I mean, that Ida storm in New York City sort of both caught people flat-footed and overwhelmed whatever was put in place already. So I think green infrastructure plays an important role in that adaptation conversation, because, a bioswale, so a pipe is only as big as the pipe is. It has no adaptive capacity other than what you built into it to begin with. Whereas a bioswale continues to offer some infiltration function even once it's full. And so I think GI has to play a role in that adaptation story, because it does have this, even if the storm the storm that occurs exceeds the design storm, because the future design storm is more intense than the historical design storm, there's still some level of adaptation that's built into these systems that isn't true of the pipes and other things. That said, you've got to build bigger pipes as well, because I think, particularly in some settings, Manhattan always comes to mind. You can't, you're not going to build enough GI into those cities unless we ban street parking, which I'll note I'm in favor of, but I know that culturally is not likely to happen. So, so I think it plays a role in that adaptation equation. That's important. So.
I want to kind of ask a follow-on, and I think these systems are great and have so much potential in a lot of places.
Yeah.
But, I get really nervous when they're like the urban planners and the landscape architects kind of go-to solution for places that may have really high water tables, or even water tables that shoot up when you get the kind of storm that Jim's talking about,
Yeah.
And at that point, I'm afraid that they, my intuition says they're not going to be worth very much, basically. And so I get nervous about the kind of deployments that are occurring. And I don't know, are you aware, are a lot of people looking at those issues of these saturation around these systems, and they're kind of not.
Yeah,
really...
I mean, I think Claire Welty has looked at some of this in Baltimore and in Philly, but I think it's a real question, right? That if you're infiltrating that water, you're turning runoff into groundwater. And if the water table rises as a result, then, you know, you could replace one problem, surface flooding, with subterranean flooding, for example. So I think that's a legitimate question and concern in certain settings. Say if you're at sea level, like, I don't know, Miami, you know, it's not gonna be as, but I think the flip side of that is that there are other ways to deal with that subterranean flooding that still, you know, you might have to increase drainage protection around structures. You know, but you do need to keep that in mind, right? And if you're in Old Town Philadelphia, you know, putting in subterranean structures isn't necessarily a cheap, affordable thing. So I think that has to be part of the planning, you know, that's present.
Yeah, and I wasn't thinking so much about the structure, the basins themselves, if we want to call them that, contributing to raising water table, but just this intense rain all around it.
Right.
You know, already bringing the water table to the surface, basically, in a whole region, essentially. And at that point, I just don't know how these things are going to work. So.
Yeah. No, yeah.
You did mention that there was a problem with like space and sometimes real estate. So would it be like a holistic approach to combine all these GI infrastructures, so subsurface, surface, and also elevated on roofs? Yeah,
I mean, I think, you know, the sort of green stormwater infrastructure I talked about, mostly bioswales, I think depending on your environment, or you're going to want to implement with other strategies, including other green infrastructure strategies, like green roofs, like and I don't know what to call permeable pavement. It's gray infrastructure, but it functions in some ways like green because it's converting runoff into infiltration. I mean, I think you want to look at, you know, Emily Bernhardt, years ago, I saw her give a talk on stream restoration in cities. And her point was, if you want to restore a stream in a city, you have to restore the watershed. And I think you have to look at whole watershed approaches to managing floods that incorporate oftentimes some very traditional large retention detention systems in combination with green infrastructure, you know, to restore the hydrograph, if you will. I mean, the goal might be put the hydrograph back what it was pre-development, but we're not in already built places, we're not going to get there overnight. And even in not built places, we're going to have to think about how to get there step by step. You know, we don't necessarily know how to do that right now. Over time, hopefully we'll build the engineering and cultural knowledge to understand, okay, here are the designs that work with the watershed design that we need to have. So.
Right. Yes, I do think that we have to keep reminding ourselves like why we need resilience and adaptation.
Yeah.
So that we can get to where we need to be. So.
Yeah, I mean, I think it you know, people don't like the answer that it's going to take us time to adapt and figure out how to do things differently. But I think that's realistic. Like, you know, I mean, I think we see it with flood response. I know that, you know, we still have houses built in floodplains, and some places haven't adapted as well as others. But there are success stories where newer development has been pushed away from stream beds and has lower flood risk, for example. Or the example of Tulsa, Oklahoma, which is a great example of sort of moving people up and out of the floodplains. Again, over time, right? You don't get everyone to move at once, but you can get adaptation over time, you know.
Great. Well, thanks for the discussion, everybody.
Yeah.
Any other questions from the team? Okay, well, not seeing anything. I thank everyone for their time today. And Jim, we'll see you next week for your presentation. Nice to see your face today, everyone. Take care. Have a good afternoon. We'll see you next week.
Thanks, Jim.
Okay, bye-bye.
Thanks, Lola.